that, the reason we're speaking today is that next year we're launching a new space technology focused track at Foresight that will be chaired by Creon Levit. That will be one of our technical tracks. And this will focus on all the way from near-term advances, really, of like what are the technologies that people are currently working on, to the more long-term question that I think Adam is really more focused on. And so today we're really happy to have a little bit of a preview into this. Usually I interview our speakers, but today we get into the very rare pleasure of actually having Creon as an interviewer, and Creon having interview Adam. So I'm really excited about this, and I will share a little bit more info about Creon and about Adam here in the chat. But as far as I know, this can go anywhere from here on. I take no further responsibility. And Creon and Adam, thank you so much for joining, and the space is yours.
Alice, I want to make a brief tie together Adam and Creon and what's going on. We and my employer, Planet Labs, we had a big day yesterday. We went public on the New York Stock Exchange, and Adam was there. So we actually just saw each other in New York City, where I still am. Are you still in New York, Adam?
Yeah, I'm at the Simons Institute at the moment.
Oh, cool. Well, I am at the hotel, so they hear Christmas music in the background. So my first question for you, Adam, is when did your interest in physics coincide with any sort of interest in space, or space, the broad concepts of space, from astronomy through astrophysics through aeronautics, any of that stuff? How did you get into physics, and did an interest in space in all its broadest sense play any role in that? Could you talk us through your history a little?
I probably arrived at physics more from mathematics than from the space angle, but some people do come at it from the astronomy angle. I lived in a very sort of gray island growing up, in which the sky was only occasionally visible. So I don't think I sort of got the astronomy bug, or maybe I just didn't have anyone to explain the stars to me.
That island was great.
Rather than directly from space.
That island
was Great Britain. Yeah.
Great Britain, yeah, I thought so. Okay.
Yeah, my development was more from mathematics and then philosophy and then into physics, at the intersection of those two, I would say.
Okay, but nonetheless, I know for a fact that at least in the past, your laptop computer, which has an apple on the cover, like so many others do, also has the apple. It has Isaac Newton's head positioned right underneath the apple. So when did you first, I know you've done a lot of studies in gravitation, and I'm wondering if you might talk how you got interested in gravitation and some of the, just a sampling of the many interesting works that you've published on the nature of gravitation.
I mean, gravitation is a fascinating topic. As you say, like, it's how Isaac Newton got his start, just making observations about apples and about the universe and the planets, and tying them together. That the same force would apply, the same force that dragged an apple to the ground also held the stars in their orbit, was quite a leap over many orders of magnitude of scale. And like that he could write down one equation that would describe both processes was a pretty seminal moment in the history of human thought. And it kind of remains relevant to this day. Like we know that there are four major forces of nature, and three of them are kind of the same and one of them kind of different. And that different one is gravity. There's weak, electromagnetic, and strong forces. All of those share lots of properties with each other, including that like charges repel. And then you've got the weird one, which is gravity, in which like charges attract. And it's also a weird one because it's just way weaker than all of the other forces. It's a force that, in order to see it and have an appreciable effect, you need to balance the apple against the weight of the entire Earth. Whereas to get a similar force from electromagnetism, you'd only need a tiny charge, And so the only reason you can see gravity is that all the electromagnetic forces basically cancel out all the positives and negatives, whereas all of the gravitational forces just add up and up and up. And so for that reason, like at the large scale, it's the most important force in nature, even though it's 10 to the 30 times weaker than the other forces, which is kind of maybe a victory for the little guy. And then like connecting it, like there's this amazing story that runs through Einstein and Einstein's general relativity, where we used to think that Newton was the final word on the gravitational force, the inverse square law, and that just turns out to be incorrect, both theoretically and now empirically. And that Einstein not only showed that there were deviations from the inverse square law, but the way he did it as a sort of cathedral of pure thought, just by having sort of thought experiments about jumping up and down in elevators. And suddenly he figured out that gravitation must actually just be an expression of the curvature of space-time. I mean, that's really an absolutely phenomenal story that I've taught and admired for a long time.
I have to unmute. And were you attracted to gravity, no pun intended? And was that your intention when you went into physics to study gravitation and its relation to other things? Or was that just a natural place to go instead of, say, low energy physics or I don't know what? I mean, you do a lot of things. You do field theory, you do string theory, you do quantum gravity, and you do quantum information theory. Is there a journey there? Can you connect the dots?
They are all connected insofar as they are the best theories we have about the world and the most fundamental theories we have about the world that exist. I mean, gravity itself, I would say that there is, well, maybe evolution, but other than that, like no story that's quite as amazing as the sort of captivating Einstein story of figuring out general relativity. You know, quantum field theory is like a beautiful subject in some ways, and is every bit as accurate as we understand it. But it was the work of many hands over many, many years. And there really is, I think, no precedent for this just sort of captivating story of Einstein figuring the entire thing out for himself and just writing a couple of papers that completely revolutionized our conception of gravity and also of space-time and our place in it. So that kind of romantic start definitely, is a sort of great beginning, I would say, for an understanding of general relativity and of gravity in particular. And then the fact that, again, just like Newton's law of gravity unites so many things from falling apples to falling planets, general relativity, it's the same. You can see the deviations in just like micro orbit of Mercury, very careful things. You can even see it in the lab, deviations from the lab when you look at the gravitational redshift of just photons bouncing around in the lab. And yet it tells a story not only of that, but also of the whole galaxy and indeed of the whole universe and cosmology and the Big Bang in a way that Newton's theory really doesn't. So I would say that, there is this story of general relativity is just like one of the most phenomenal stories the human race has ever told.
I just recently read a beautiful book on the flight to New York from San Fran by Tristan Needham, who's actually a professor of mathematics at UC San Francisco, at University of San Francisco, called An Introduction to Visual Differential Geometry and Forms. It's in 5 chapters, and the 4th chapter is general relativity explained in a way that is probably the most beautiful that I've ever seen, including Misner, Thorne, and Wheeler, which of course he draws heavily from, but he's just going for that one bit. So Visual Differential Geometry and Forms by Tristan Needham. Adam won't need this book, he knows all this stuff, but for anyone who's trying to level up their understanding of general relativity, go for it. So as you know, Adam, I mean, general relativity has implications for let's say gravity theory has implications for just pedestrian space travel, like just, missions to Earth orbit, missions to the moon and stuff like that, and through the solar system. It also has implications that go far beyond for the large scale structure and deep future history and past history of our universe. You've published a number of papers on sort of implications of gravity to various potential human technologies. Might you discuss some of these?
Happily. So I think maybe one paper that I wrote about was this black hole mining story. And I wrote about that in a physics journal article, but I also wrote about it, did a write-up for Scientific American. If you want to read about it, you can find it there online. And that's a pretty fun story. So the question I was looking at in that paper was, can we get energy out of black holes? And you could imagine a sort of sci-fi future in which we really want to use the energy that's in black holes. And so the question is, can you get it out? And there's a kind of old story due to Penrose about how to get energy out of black holes, which is that if you have a spinning black hole, black holes, just like humans, can have angular momentum. If you have a spinning black hole, you can kind of bleed off that rotational motion using some complicated apparatus, or not so complicated apparatus if you do it right, and extract the energy in that way. But the energy there you're extracting is really the sort of kinetic energy of the black hole. It's not really energy stored in the black hole itself. And so at the end of the day, you have got energy and you're left with a stationary black hole that's not spinning anymore. And once it's not spinning anymore, you can't extract any more energy from it, or at least you can't extract any more energy from it using the Penrose process. It's sort of dead and inert. And so can you extract energy from a stationary black hole? Non-spinning was the question I was looking at. And at kind of first, it seems a pretty difficult prospect, because black holes famously have this property that once you're in, you can't get out. So any attempt to extract the energy from the black hole must surmount that barrier. And indeed, there's a classical story in which it's impossible. It's just like this impact theorem due to Hawking, that there's no more energy to be extracted from a stationary black hole. However, there's also a later theorem due to Hawking that the first theorem only applies if you ignore the effects of quantum mechanics. And if you include the effects of quantum mechanics, in fact, you don't even need to do anything. Energy leaks out of a black hole. It just leaks out extremely slowly, basically for the reason that quantum effects are tiny. So if you take a solar mass, if you take a solar mass black hole that weighs the same as our sun, then you'll find that it has a heat temperature of 60 nanokelvins, which is obviously too small to discern. But nevertheless, over the eons, 60 nanokelvins radiating according to the Stefan Boltzmann law, energy goes out, and because of E equals mc squared, that means mass goes out. And so gradually, you'll radiate away all of the energy that used to be in the black hole. So if you start off with a solar mass black hole, it'll eventually radiate away all its energy, and that'll take a long time. And the time it will take is 10 to the 55 times the current age of the universe. So really a sort of exceptionally long time. And the paper I wrote was investigating the question of whether this process might be hurried along and whether we can extract the energy faster. And as Creon mentioned, actually there's something that helps you, which is that as black holes radiate, as they lose energy, unlike most things, black holes have the opposite property, where as they lose energy, they actually get hotter. So as the mass goes down, the temperature goes up. So it kind of is a bit of a runaway process, and the very end of it is fast, and you just get a kind of explosion of the black hole. In fact, the original Hawking paper that discovered this was called Black Hole Explosions ? And proposed that we could look in the sky for these remnants of a black hole, just going off right at the very end with the force of a million nuclear weapons.
Okay, I have several questions stacked up here. First, I'm going to state them in order, and then you can wander around as you desire between interpolating or extrapolating. Question one, you published a paper, the Scientific American paper, and its peer-reviewed ancestor that suggests a way that it might be possible to mine this energy at a greater than natural rate, as I recall, or at least in some way to make it useful, more useful than just a heat engine. And then the second question is going back to your discussion of the Kerr solution for the spinning black holes. When I was a child, I read in a semi-popular book that these spinning black holes can allow time travel or even travel to alternate universes. I'm wondering if that is still a thing, or are there now theorems and new results that say that was going a little too far? So the question of the spinning black holes and time travel and travel to quote unquote other universes. And then the last question is going to be, how strong do you think the evidence is for the actual existence of black holes in our universe, and how has that evidence accumulated and changed over the years?
Okay, thank you, Grant. So there's questions about mining black holes in there that I'll get to at the end, and then there's questions about black holes themselves. Yeah, so first of all, you asked, can you build a time machine using a spinning black hole? And you're right that people have looked at that topic, and there are sort of intriguing closed time-like curve-looking things inside the solution for a spinning black hole. According to physics as we currently understand it, we cannot build a time machine from a spinning black hole. You can come close to building a time machine, but close to building a time machine is still ends you up with no time machine. So according to physics as we understand it, it is not possible to build a time machine using spinning black holes. It is the case that there are speculative theories of physics that would permit you to construct a time machine in various ways, and some of the ingredient lists involves highly spinning black holes. But at the moment, and actually that's a good thing, because I was just about to describe, there probably are some highly spinning black holes in the universe. But at the moment, there's no, yeah, I mean, according to physics as we understand it, time machines cannot be built by us.
So
Okay, that's question one.
Wait a minute, there was this thing called the chronology protection conjecture that basically assumed that you can't have loops in time that cause paradoxical processes. How does the chronology protection conjecture relate to the claim that you made that we now believe physics prohibits the construction of time machines at all? Could we construct time machines that have non-paradoxical solutions like that, where the grandfather paradox is avoided, but you still can do time travel, or is time travel just simply out?
So first of all, you chose a carefully chosen phrase, which is you cannot construct a time machine. There is nothing in the laws of physics as we understand them that prohibits you finding a time machine if one was pre-existing, or whatever the word pre means in that context. But it's the construction of time machines that seems to be forbidden by the laws of physics as we understand them. That's point one. Point two, the chronology protection conjecture is a conjecture that was formulated in response to a number of thought experiments in which people tried to build machines that would produce time machines, and then sort of bugs were found in them that they didn't work. And you can either think that these bugs are a sort of annoying coincidence, or you can think that these bugs are getting at something deeper. And I think probably the latter is correct. And so the chronology protection conjecture is not the reason to believe you can't build time machines. The reason to believe, it just summarizes the fact that every time we've tried to make one, or at least think about making one in the thought experiment, it sort of never works. There's always something wrong with them. And usually the thing that's wrong with them is that they violate something called the null energy condition that we believe is inviolable. So, but like there can't be a mathematical proof. There's just, according to the laws of physics as we understand them, one cannot do it. Okay, we were sort of ramifying with all the questions. The other question you said was like, do we believe in black holes? So there's kind of two trains of evidence for the existence of black holes. So black holes were sort of a prediction of general relativity, of Einstein's general relativity, and he found it in 1915. He finished this theory, this sort of beautiful theory. And actually, the idea of a black hole predates Einstein. I think it was Laplace who says, if you have a maximum speed, then a sufficiently heavy body will have a escape velocity greater than that maximum speed, even in Newtonian physics, and therefore you can't get out. Now, exactly how rigorous that argument is isn't totally clear, because I don't need to tell you, Creon, but rockets manage to escape the Earth without ever exceeding the escape velocity of the Earth, or at least not while they're nearby. So from a Newtonian point of view, you might think, well, maybe you can't have escape velocity all at one go, but you just keep firing a rocket as you go along, and eventually you can get out. However, in general relativity, that turns out not to work. And basically, the reason it doesn't work is because all that rocket fuel that you're planning to use later is going to weigh you down even more so than it does in Newtonian physics. And this really is a totally impossible to get out. Okay, so this is this consequence of Einstein's relativity that he didn't really understand, I would say. He struggled with it and wrote a number of incorrect things about black holes. And in fact, the black hole solution wasn't found by him. It was found by Schwarzschild like a few months later, who was a Prussian artillery officer on the Eastern Front, who discovered as a consequence of Einstein's theories that there was this prediction for a black hole should exist, and then promptly expired. And that was kind of his legacy, was this prediction, and then that prediction kind of sat around for 100 years, and we accumulated various pieces of evidence, but it was mainly just the sort of theoretical compellingness of the existence of black holes that was driving our confidence that black holes exist until very recently. And very recently, we have 3 different pieces of evidence, experimental evidence that black holes exist. And one piece of evidence of that is these telescopes that look at the center of our galaxy. And at the very center of our galaxy, there's Sagittarius A star, which we believe is a 1 million solar mass black hole, a black hole that weighs 1 million times what the sun weighs. And we look at it through our telescope, and when you look at it, you see absolutely nothing, because it's black, notwithstanding the comment I make about 60 nanokelvins. You definitely can't see that. It looks black through a telescope, so you can't see it. But what you can see is all these stars that are not black in the middle of our galaxy, and they seem to be orbiting something. And so we watched them through these telescopes for 3 decades now. And during that time, they seem to be orbiting something, and they have not quite elliptical orbits. They have something else orbits. And that something else orbit is, in fact, a deviation from Newtonian physics, exactly what will be predicted by Einstein's general theory of relativity, that you get a deviation from elliptical orbit. And then we've watched them, and you can watch the video online. It's really impressive. All these things come in, and you're looking at it, and you're like, well, I can't see anything in the middle of that, but I'm pretty sure there's something there. And you can back calculate from the orbits what the mass of the object that's there is, and the answer is it's 1 million solar masses. And you can calculate the size just by seeing how close the orbiting star gets without falling in, or the orbiting stars. And sure enough, you find that you have 1 million solar masses crammed into a completely black, invisible, crammed into a region that's really not much smaller than the size of a black hole would be. So there's really not much else it can be, except for a black hole, one would have thought. So that was evidence number 1, and that's been accumulating over the last few decades as we've just been watching these stars execute their orbits around something in the middle of the galaxy. That's evidence number 1, and there's 2 more pieces of evidence. The second piece of evidence kind of made a fool of me. I taught the general relativity course at Stanford and devoted 20 minutes of the last lecture to gravitational waves, and then a month later they announced the discovery of gravitational waves, which was previously just this this subfield of detail on general relativity, and suddenly became our biggest piece of evidence that's possible. And in September 2015, we felt the collision of 2 black holes. The black holes has actually collided 1.4 billion years prior, but they collided 1.4 billion years prior, 1.4 billion light years away. So it had taken that long for the influence to reach us. And this was the discovery of gravitational waves, for which a Nobel Prize was subsequently awarded. And 2 big black holes sort of spiraled in and then collided. And a prediction of general relativity is that when 2 black holes collide, or in fact, when anything collides, it'll not only emit electromagnetic waves, like if you smash 2 things together, they'll give out light, actually it'll also give out gravitational waves. But because gravity is so weak, you need to get really, really heavy things moving very, very fast. And this was things that were dozens of solar masses, black holes at dozens of solar masses moving at basically the speed of light, smashed into each other, out-propagated the gravitational waves at the speed of light, and we felt it. We felt the sort of shock. And the reason we felt it is because we were ready. And there was this thing called LIGO that the National Science Foundation have been funding for many decades without any success. And they finally had their big moment. They were ready for these gravitational waves that came in. And they, in 2 sites, one in Hanford, Washington, and the other in Louisiana, had set up an incredibly intricate array with lasers going back and forth and doing a laser interferometer. And that could measure deviations in the length of the arm. So two laser arms at each place, each of which is 4 kilometers long. And they could measure the length of that 4 kilometer arm with these lasers using an interferometer that would change by no more than 1 part in 10 to the 22, which is a very small deviation indeed. So you have a 4 kilometer long arm with a laser going back and forth. As the gravitational wave passes, as the shudder in space-time passes, that 4 kilometer long arm becomes 4 kilometer plus 1,000th of the width of a proton, which is a very small amount indeed. But nevertheless, such is the state of laser interferometry that they could measure that and detect gravitational waves. And it was this great triumph. And so that, I mean, after that, I would say that you've got to be pretty highly confident that black holes exist. Like absolutely every aspect of the theory, including the gravitational wave, was then tested. But that wasn't the end of it. There was then like 1/3 piece of evidence that came out maybe 3 years ago now. And that is they took a big radio telescope. So this is what I'm describing as like 3 completely different ways of looking at the universe. They took a big radio telescope called the Event Horizon Telescope and took a photo, a radio telescope photo of the black hole at the center of a neighboring galaxy, which is actually a billion solar mass black hole. And then you just see the kind of light field, and then in the middle there's blackness, it's inky blackness, and you're meant to think that that's, so you're actually looking at sort of the backlight of the accretion disk, and then there's nothing in the middle, it's just black, which is meant to be the black hole. So those 3 sort of super impressive pieces of evidence. I was already convinced by Einstein, but if you were from a more skeptical empirical bent such as yourself, you now have excellent empirical reason to believe in the existence of black holes.
So those black holes, the one at the center of our galaxy, the one that was, well, as I understand it, there are a number of ways black holes can be created. They can be created by a massive enough star that collapses. And we're pretty sure that happens, although I don't know if we have direct evidence. They can be created from the mergers of other things, including things that aren't black holes, like sufficiently massive neutron stars when they collide. There's some evidence for that. They can merge and create a black hole. And then there are these ones at the centers of the galaxies, which, as I understand it, we don't really know where they come from. Do you have anything more to say about those 3 genesis for different kinds of black holes? And are there other possibilities for the universe to create black holes outside of technology?
Yes. So the black holes, our sun will never be a black hole, probably, because it's too light. It's only 1 solar mass. But if it was a bit heavier, if it was like a 5 solar mass black hole, then at the end of its life, after it had burnt everything up, it would start contracting because it's being held up by the pressure of all of the hydrogen turning into helium that it's creating. And then it'll get smaller and smaller and smaller and more compressed. And then you start burning helium into heavier elements, and eventually that process is done. You've burnt all of the things you can burn, and there's no more radiation pressure, and so it'll collapse. And if it's as light as the Earth, that'll just be the end of it. It won't collapse all the way. It'll get stopped by the degeneracy pressure, just the desire of the matter in it not to get crushed all into one state, and just the pressure of that state. But if it is heavy enough, it'll form a black hole. And so that's like the classic way to make a black hole. It's end of life of very heavy stars that maybe end in a supernova, in which they slough off all of the stuff at the outer edge, and the inner edge becomes a neutron star or even a black hole. So that's the classic way to make a black hole, and that way is probably the way that the black holes were made that we then heard collide or felt collide through the gravitational waves. But that tends to make black holes that are sort of 10-ish, 1 to 30 solar masses. The black hole at the center of our galaxy is 1 million solar masses. And it's not totally clear how that was made. And that is definitely a subject of active inquiry. I mean, you can understand how it grew, but like quite whether it had time, according to our current understanding of the history of the universe, to grow that big in that length of time is something that astronomers spend a lot of time worrying about. And that, those questions, as you said, about like primordial black holes as well. I can't hear you, Creon. I also see that. I also see that people
asking questions. Yeah,
asking questions. But maybe you want to moderate those too.
I'm gonna try and do both. I'll be putting my glasses on and off, I guess. So so before I get to the questions from the audience, one more, which is, you've made some rather bold statements about things that are within the realm of possibility, within the laws of physics, and hence within the realm of possibility of a sufficiently advanced civilizations. So that would be another way of making black holes, and probably not time machines, but possibly other things. Might you speculate about some of the far future or possibly even present technologies that might be the result of advanced civilizations who have mastery of general relativity or even quantum gravity or things beyond the standard model? And then we'll go to the audience questions.
Yeah, so one, aspect was the story that I started at and didn't finish. I set up the idea that one might wish to accelerate the process of extracting of energy from black holes, but I didn't describe how one might do it. And my work was sort of looking at an obstacle one would face if one wished to do it, which is there's a sort of general plan, which is that you go in there and kind of, so it turns out that these black holes that are radiating, albeit very weakly, they actually radiate a lot of energy, but the energy just sort of falls back into the black hole again. That's a feature of them. So the reason that they give us such a small temperature if they're a long way away isn't that they're not emitting energy. It's that they emit energy and then the energy just immediately falls back into the black hole, which I guess makes sense if you know how strong the gravitational field of the black hole is. And so this quantum process actually allows you to emit energy quite a lot. And so there's a kind of idea, which is you go in there and grab the energy that's just made it out of the black hole and then rescue it before it has time to fall back into the black hole. That's the sort of general set of proposals. And my points were, well, okay, first of all, let's talk about how we're going to grab that. You better plan not to be to just go fly by in a rocket and just grab it and then keep going, because your rocket will fall into the black hole if you do that. And the only way it won't fall into the black hole is if you fire your rocket engine really, really hard. But then you can calculate it, and your rocket fuel will then fall into the black hole as you eject it backwards. Will totally obviate all of the benefit you might have accrued by grabbing that radiation from close to the black hole horizon. So that's a complete non-starter. You might hope to build a Dyson sphere to sort of grab it and then just shoot it, but that you absolutely cannot build Dyson spheres that close to black holes. There's nothing possibly strong enough to maintain a Dyson sphere around a black hole. And so like another proposal would be to build essentially a space elevator. So buildings are sort of, skyscrapers are supported from below, where the below pushes up and keeps the rest of the building up. That is a sort of absolute non-starter around a black hole, because you can't put a foundation into the black hole, but you can sort of reach in and dangle something, not a compression structure, but a tension structure down from above, and hope to grab something up. And so, because this is this plan to do launch more cheaply on Earth, is rather than use rockets, which are pretty wasteful according to the rocket equation, you just dangle a space elevator down from space, and then it isn't supported from below. It's not a building. It's a tension structure, and then you can just sort of climb up. And in principle, once the space elevator has been built, the marginal cost of getting to space is just you just put a little electric motor as efficient as you like, dragging stuff into space. So that's kind of the old space elevator plan for Earth. And the problem with the old space elevator plan for Earth is that whatever this space elevator is made of, it needs to be strong enough to support not only the object that's trying to climb up it, but also its own weight. And that's very hard because you calculate, the tensile strength of steel, let's say, and it turns out that it's just like steel is just not nearly strong enough to do it around Earth. You need to, because to support the weight below it, you need to make the bit above it a bit thicker in order that it's below it plus its own weight, and thicker and thicker and thicker, and kind of tapered thicker and thicker as you go up. And you can run the calculation, and the amount of steel you need around Earth needs to be the thickness of the Earth, basically, by the time you get to orbit. So it's a complete non-starter. But for carbon nanotubes, people talk about, because carbon nanotubes have a great tensile strength to weight ratio. That's the figure of merit from material science point of view. The weight is how much is the problem, because you're being dragged down by your weight, and your tensile strength is the solution because you're being pulled up. So the figure of merit for your material is tensile strength to weight ratio. And people talk about carbon nanotubes, which at the moment just exist in labs, including one there where I'm sitting right now, that are only centimeter-ish in length. But people talk about building the 40,000 kilometer long strands of carbon nanotubes that, and if you could do that in a predictable way, you could in fact build a space elevator around the Earth. But of course, from my point of view, the Earth is a reasonably easy test case, and now we're trying to build it around a black hole, which is a significantly more difficult proposition. And carbon nanotubes just absolutely won't work at all around a black hole. They're just not nearly strong enough to build a space elevator around a black hole. And you can just a simple calculation will convince you that if you try and do it around a black hole, the carbon nanotube near the point here, near the black hole end, needs to be pretty thin. But it can't be too thin, because if it's too thin, then like even a 60 nanokelvin photon coming in will melt it. So it needs to be like there's some just tiny little, it can be very, very thin, but not like infinitesimally thin. And then you can just sort of follow it as it goes up, and it has to get wider and wider and wider. And in fact, if you try and do it around a black hole, what you will find is your carbon nanotube has to be so thick by the time you get sort of away, the other end at the top, that the carbon nanotube will itself have to undergo gravitational collapse and form a black hole, according to Einstein's theory. So basically, carbon nanotubes are out. And the question that I was investigating is like, what's it? Is it possible to do it? And then it turns out that actually, even though physicists don't usually think of it this way, this property of having a tensile strength to weight ratio is in fact bounded by the laws of physics. In fact, it's bounded by the null energy condition that I mentioned before. There is a maximum possible tensile strength to weight ratio of any rope that's consistent with the known laws of physics. And if you calculate all the units, that's actually just got no units, or if you like, it's got units of 1 over the speed of light squared. And so that's just some number. That's some number of newtons per kilogram per meter of tensile strength. And it turns out that that is in fact saturated by a hypothetical entity that I spend a lot of my time studying, which is a string. The strings made famous by string theory are in fact as strong as any possible rope can be according to the laws of physics. They saturate this bound. And so, well, what does that mean? One, that means if you want to do it, you need to use strings or something with the same tensile weight, strength to weight ratio as a string, which kind of makes it a string. And the other thing is that strings only marginally can do it. They're exactly on the edge of just being able to do it, which is to say they have just enough strength to support their own weight, and therefore, sadly, no strength left over really to support the weight of the cargo that one might wish to lift up. So,
okay, Adam, hang on a second.
Okay.
So what you're saying is that in theory, if string theory is correct, and if we could build things directly out of strings, we might be able to build a space elevator that would be able to reach down through the event horizon of the black hole. Is that what we're talking about here? And
well, it couldn't recover anything from behind the event horizon. It could reach very close to the event horizon. I mean, it could reach basically as close as you like to the outside of the event horizon.
Okay, but is it not the case, and this will be the last moderator question before we turn over to audience questions, and I'll try and manage them. And if I can't, then Allison will. But the issue is it not the case that if you are around a supermassive black hole, like a galactic center black hole, you don't even notice when you're passing through the event horizon locally that the event horizon is, while it's a big deal for those from the outside, you could have an event horizon where the forces don't even feel that big to you. So why couldn't you extend the string into the interior? Is it just because the exterior would have to be too large to avoid collapse, or what's going on here?
Yes, you're right. So black holes, two important places to know about in a black hole, one of which is the singularity at the center. That's at the very center. It's a point-like singularity in which everything has collapsed down to a point. And by the time you reach the singularity, then you're definitely dead. Like that'll kill you, the spaghettification, as they call it, infinite tidal forces, all the rest of it. As you say, the horizon is not singularity. The horizon is considerably further out. The extent to which it's further out is proportional to the size of the black hole. But for the billion solar mass black hole at the center of our neighboring galaxy, that's quite a long way out. That's about a billion miles actually. So that's got like quite a long time before you hit the singularity. I mean, you're traveling at almost the speed of light, so not that much time, but still like long enough to be upset about your predicament. And the tidal forces also drop off with distance. The same tidal forces that will spaghettify you when you get close to the black hole drop off. In fact, there's even worse than an inverse square law. It's drop off like an inverse quartic law. So if you get far enough away, you don't have to worry about the tidal forces. And the tidal forces for a large enough black hole can be very moderate indeed as you cross the event horizon. The event horizon is when you're doomed, but not yet dead. And your question was, why can't you lower a space elevator across the event horizon, given that it's not a locally significant matter? It's a kind of teleological surface in which it's the point of no return, but it doesn't say the point of no return. You just cross it, and then it turns out there is no return. And the answer is you absolutely can lower your space elevator across the event horizon. There's not a barrier there that will stop you. The only problem is not that you can't lower the space elevator across the event horizon, it's you'll never get it back. And that is itself a teleological question, whether you'll ever get it back, rather than something you can locally measure. It doesn't change color when it's doomed.
Okay, so now switching over to the switching over to the audience. Let's see. Let's do these in the order they were posted. These are sort of random physics questions, not specifically related to this. And the first question is, how, if we're moving them, I'll just read it and not try and recast it. They might be opposed. If we are moving slower than the speed of light, how is it possible that we would see the afterglow of the Big Bang? The original light of the Big Bang would have passed us long ago.
So that is right. So the Big Bang, 14 billion years ago, and there was a explosion that made the universe as we know it. But the slightly tricky thing that helps answer your question is you shouldn't think of the explosion as having happened at a single point that just shoots everything out. You should think of it as, in some sense, having happened everywhere. So in answer to that question, it happens across a whole spatial surface at once. I mean, if you know general relativity, it's gets slightly trickier than this, but that's basically correct. So while it's true that the bit of the Big Bang that happened here in the current location of the Earth passed by us, the shock wave from that passed by us 14 billion years ago, there's a bit of the Big Bang that took place what's now 14 billion light years away that's hitting us now. So that's the answer to that question.
Another question from the audience is, I'd like to hear how Adam's work relates to humans actually getting into space and what we can and can't do once we get there. And this is a good one, Adam, because you've discussed, at least I don't know if you've published on some more sort of pedestrian questions about gravity and space travel, right? And you're muted.
Yeah, that's right. I mean, as time passes, we have discovered that the gap between physics and engineering, particularly the gap between high energy physics, my subject, and engineering has widened from maybe just 10 years in the 1930s up to today. And it's absolutely true that we're not running up against these fundamental limits, I would say, anytime soon. There's a long way to catch up between what we now know to be physically possible and what the engineering frontier is. I think another way to think about it, though, is that all of these problems that we have are sort of the problems that we have in these engineering endeavors do tend to be pretty closely linked back to sort of fundamental physics scales that arise reasonably naturally from fundamental physics. So if I just think about why is getting off the Earth hard, the reason that getting off the Earth is hard is because the electromagnetic force is so weak compared to the strong force, and then subscales about gravity in there too, which means that if you're just using chemical rockets rather than the nuclear rockets, the fact that electromagnetism is weak, that alpha, this factor that controls how weak electromagnetism is, the fact that that's small just means that if you have a proton, only one part in, the binding energy of a proton, the weight mass of a proton is a billion electron volts, and the binding energy of a electron around a proton is a few electron volts, depending on how you do it. And that means that chemical rockets are only ever going to be able to give you an energy equal to 1 part in 10 to the 9 of their rest mass. And that ultimately is the problem with getting off the Earth with chemical rockets, for example, because that also describes the gravitational, the difference in gravitational potential between the Earth's surface and outer space.
Okay, so I'm going to skip forward because there's a number of questions about exploiting black holes, but then there's someone who says provocatively, this seems like a fantasy discussion, taking foresight to the ridiculous extremes, since the nearest black hole is 26,000 light years away. Gathering its cast-offs might be far in the future, and we might no longer be humans at that point. Do you think that the practicality of some of these things, as well as your even more speculative things that you alluded to at Foresight about mining the cosmological constant, which you get to, are these just thought exercises, or do they have any relevance to a real future?
Yeah, first of all, it's probably not the case that the nearest black hole is 27,000 light years away, which would be sort of near the center of the galaxy. There's probably black holes much closer than that, but at the moment we haven't seen them. So there's the black hole in the center of the galaxy, and there's also black holes that are formed from stellar collapse, which are much smaller and closer. We just haven't seen them. But I think the spirit in which the question was asked probably would considering the distinction between 26,000 years and 26 light years to be quibbling. Yeah, I mean, I think it's an interesting question. If one looks at the exponential growth in technological progress, I don't think it'll be forever before we hit this. There is a question about whether that growth will continue, but these limits on a log chart are not so far away. But for the moment, yeah, they're definitely the thing that's our ability to build rockets is not being impeded at the moment by speed of light considerations.
Okay, so I'm going to ask a follow-up on that, which I think is relevant, and I've never asked you this before, but that is, and just for the sake of full disclosure, I ask Adam physics questions about as often as he will permit me. And he usually gives pretty good answers. My question is this. We have the standard model, and then we have extensions to the standard model like string theory and quantum gravity theories, and evidence for physics beyond the standard model, like fine-tuning and dark matter and dark energy. Do you think we will ever be able to build a warp drive and kind of obviate some of these, using either the standard model or beyond, and obviate some of these objections about long distances making things impossibly far away, both in space and probability space?
Yeah, so warp drives actually have a lot in common with with time machines, which is to say there's certainly nothing in the laws of physics that prevent them pre-existing. But if you want to build one, that's a very hard thing to do, and almost certainly requires you to violate the null energy condition, which is this sort of same condition that keeps cropping up as the villain of all of these stories.
But doesn't the cosmological constant or the dark energy possibly violate the null energy condition? And isn't that most of the universe?
Not according to the laws of physics as we understand them. According to the laws of physics as we understand them, it's the dark energy, the thing that's causing the current accelerated expansion of the universe, has some number, it's called the equation of state parameter of -1. And -1 is exactly saturating the null energy condition. That's just sitting exactly on the edge. It does not violate it. So I guess the hopeful, from your point of view, way to say it would be, well, if you're exactly on -1, just a little nudge will get you less than -1. Another point of view would be, no, that's the limit, and it shouldn't be a surprise that things right up against the limit, but they can never go faster than the limit. For example, I mean, very analogously, there's plenty of things that go at or very close to the speed of light out there, like photons. That does not mean that just a little nudge will get them to go faster than the speed of light. Like the situation is exactly analogous.
Okay, so Brad asks, what if we put a big laser in orbit above the event horizon and it receives the energy and shoots it out as light?
Yeah, so that's a good question. And the answer is no. The answer is no, you cannot be in orbit that close to a black hole. So this is actually sort of an interesting illustration of this principle of general relativity, which is that all energy gravitates, not just rest mass energy, all energy. Kinetic energy gravitates, everything gravitates. So you may wish to orbit a black hole. And so your strategy when you're orbiting the black hole is that, if you get closer to the black hole, the downwards force of gravity gets stronger. And you're going to fight that downward force of gravity with a centrifugal force by putting the spacecraft laser platform in orbit. And the idea of the centrifugal force is that, as things are whirling around, they get shot out. In fact, according to general relativity, both of those are fictitious forces. So you're fighting a fictitious force with a fictitious force, which sounds good. But there's a problem, which is there's a third effect that happens that's not present in Newtonian physics and is only present in Einstein's general theory of relativity. So with the International Space Station, you know that the faster you go, the more the centrifugal force pushes away. But in general relativity, there is that effect, but there's another effect, which is as well as the gravitational attraction of the laser to the black hole, you also have the gravitational attraction of the kinetic energy of the laser to the black hole. And so that means that actually, if you get close enough to the black hole, going faster in a circle is actually counterproductive. It's counterproductive because once you're inside a certain radius, which is 3 GM for those keeping track, the increase in gravitational attraction towards the black hole caused by your orbital kinetic energy exceeds the centrifugal force and actually makes it harder rather than easier to escape the black hole.
Okay, sorry for the pause.
And sorry, Brad, I see asked a follow-up question, which is as close as you can get then. Yeah, unfortunately, you can't get that close. You really can't get that close at all. You can get down to a short shot radius away from the horizon, but it's hardly hotter there at all. All the energy that sort of escapes from a black hole and falls back in happens very close to that horizon. So you can't really get meaningfully close to a black hole, unfortunately.
So someone asked about the possibility, and this is pretty cool. What about technologically creating micro black holes and utilizing them for something? There's been science fiction written about this. I think in the 3-body problem, among other places. And so, is that a possible thing? Or
yeah, so here's one recent proposal along those lines. Well, this is an old idea, but it sort of didn't work. But anyway, now maybe the new version does work. So if you want to, a fundamental problem with trying to extract energy from anything is baryon number conservation. So what that means is that if you have a, as I described, like chemical energy is extremely weak because of because the electromagnetic interaction is so weak. But even nuclear energy is kind of pretty weak. So if you do uranium fission or fusion and ask what fraction of the energy of the MC² energy of the fuel you're getting out is, it's pretty disappointing. It's sort of sub% level or even less than that for fission and for fusion. And the reason it's sub% level is that now you're not only extracting the energy in the electromagnetic force, you're also extracting the energy in the strong and weak nuclear forces in these things. So you get to extract much more energy. But actually, most of the energy, well, in the manner I'm about to describe, most of the energy isn't in those forces. Most of the energy is in the rest mass of the protons and neutrons that's making up your nuclear fuel. And so that's kind of disappointing. That's why that's not accessible to you. And the reason it's not accessible to you is you can turn protons into neutrons or neutrons into protons. You're not allowed to turn protons into not protons or neutrons. That number is conserved by electromagnetic processes, and it's conserved by nuclear processes, and that's why you'll never get a beautifully efficient, multiple tens of percentages efficient nuclear rocket. It just can't. It's just not good enough. But there is something that can do that for you, and that's actually black holes. Black holes do not respect baryon number conservation. If you throw a baryon into a black hole, it'll just, a baryon is a proton, for example, it'll eat it up and then spit out through Hawking radiation the energy, but that energy will not be spat out as baryons anymore. It'll just be spat out as electrons and more to the point, photons and gravity waves that'll just get sort of splayed out. And so that's actually great. I mean, from the point of view of trying to harness what is otherwise useless energy in spent nuclear fuel, whatever you've done, once it's iron, you've basically extracted all the energy you can. And then you throw it into a black hole, or even better, slowly lower it into a black hole, and you can actually extract 100% or close to 100% of the rest mass energy of these things. So that's way, way better than anything that doesn't involve black holes, basically. And so that would give you, I mean, that's essentially as good as a matter-antimatter drive, except you don't need to find the antimatter. You can kind of just make it by lowering something towards the black hole. And that gets you close to 100% MC² efficiency. And so there are these proposals that we make sort of, in order to harness that, we make microscopic black holes. And then we use the microscopic black holes to sort of chew up energy in this way. I mean, there's a risk, honestly, which is that if you do it and it kind of gets a bit out of control, and you lose control of the black hole, that can be bad for the safety of the planet. But there are proposals to do it in space or somewhere where even if something went wrong, we might be okay.
Okay, so we're running out of time, as I understand it. So maybe we'll close with the final question, which is, what's the question that I forgot to ask? Is there something that you would like to tie this up with, or leave us with as a springboard to some possible future conversation, which I hope we have?
Well, something you haven't asked me about is taking these ideas for what you can do around black holes and then applying it to the universe writ large, to the cosmological constant itself. Which, if this is a problem that we will eventually face, is that we use up energy and then we don't have it anymore, or if it falls across our cosmic horizon, we certainly don't have it anymore. And even these black holes, once we've mined them, they're mined and they're all mined, and then there's no black hole left. And so eventually, if we really are to live forever as a civilization, we're going to have to figure out how to mine the cosmological constant itself. And that doesn't seem to be inconsistent with the laws of physics. It doesn't even seem to be inconsistent with the null energy condition that I mentioned. But we're just going to have to get pretty sophisticated about it. But thankfully, we have a few billion years to figure it out.
Okay, Adam, thank you so much. It's always a pleasure talking with you, and it's at least as much of a pleasure to talk with you in a public forum. Allison, is there any housekeeping we need to end this? I'll hand it over to you.
Well, I just want to thank both of you. I think we couldn't have asked for a better start into the holiday than this. Pretty yeah, eye-opening to say the least discussion. Thank you so much, both of you. I really, really appreciate you taking the time to talk about this. And yeah, if we achieve only a fraction of the things that we just laid out, I think we're already to a pretty good start in our civilization. So thank you so much for joining and for sending us off with a little bit of existential hope into the holidays. So
Yeah,
thank you, everyone.
we'll check in a few billion years, Adam, or perhaps sooner.
On Zoom, obviously. All right, everyone, have a lovely holidays.